Hello, Craig Yambor here, detailing my modified action-reaction rocket activity. In this activity, students construct from simple items rockets that are propelled along a guide stream. They use this model to learn about Newton's 3 laws of motion, examining the effect of different forces on the motion of the rocket. Their challenge is to be able to develop a method for ensuring the rocket can move a short, medium, and long distance. As you can see on the chart, it's targeted for grades 7 through 9. I upped the activity time to 90 minutes. The cost is minimal as the materials are simple. Group sizes of 4 work really nicely. Dependency has none, and it's in the area of physical science. As for key modifications, first I reoriented the activity around a key guiding question or challenge instead of using set procedures. I added opportunity for groups that were struggling to complete sections of the worksheet and trade that in for process suggestions or tips. I oriented the worksheet packet to align with all these updates. Updated assessment section including a suggested formative measure, created full answer key, and added additional materials to allow some creativity and alternate solutions. How does the activity line up with STEM practices? Well, as for a coherent set of standards, that depends on how you work this in a curriculum, but certainly Newton's laws of motion are big ideas that should be addressed at the middle school level. As for teachers with a high capacity, again, that's dependent on who's actually presenting. For the supportive system of assessment and accountability, this activity does include documented pre-activity research questions, during activity data capture, and post-activity analysis and justification questions. As for adequate instruction time, I did mention that I upped the time to 90 minutes. I felt as I added in some of the pre-research activities and the post-analysis and discussion activities that an additional period or another 45 minutes would be justified. Looking at how the activity falls on the inquiry continuum, I did switch this to be a completely teacher-guided question. Looking at how learners give priority evidence, I felt this was very learner self-directed. As for learners formulating explanations, there's a lot of variation here. There is some opportunity for learner self-directed, but I did leave an option for obtaining guidance from the instructor, and I did provide a data template to help guide what type of analysis data should be captured. As for learners evaluating their explanations in light of alternate explanations, I felt as this activity worked out in a classroom, each group would have slightly different results and slightly different angles that they came at it from, and this would be a great opportunity for those discussions to occur. And then finally, in the same light, the learners could communicate and justify their proposed explanations. For those of you who have had class with me before, you know that I turned to the 7th and 8th graders right here in my own home as the examples. Here you see Marley and Luke digging into the research questions at the beginning of the packet. Those questions help out with Newton's 3 laws, how action and reaction forces interact, and get the team thinking about key design principles that they can bring to their model. In this video, we see as the team jumps right into modeling and prototyping. They tested and fine-tuned components, then built the final model. Like all good engineers, as their model came to final form, they decided to capture their design. Here you see that they've depicted 2 different views, and then 2 versions of the one view where the balloons were both inflated and deflated. And finally, they included, as requested, the action and reaction forces. In this early attempt, we see as the team struggles with some exhaust plugs made of pipe cleaners that leaked. Ultimately, those exhaust plugs and the release mechanism are abandoned. The home team here handled this activity no problem on their own. But for groups that might struggle a little bit, I took the original procedure steps, divvied them up into tip sheets, which could be metered out for those groups that need a little extra push. This team identified they wanted to regulate the propellant to adjust the trip length. They developed a method for measuring how inflated the balloons were. Then they tried some 4-inch inflation runs, but did not like the really short runs they got. Here they execute a 6-inch inflation run and come to agreement on how to capture each trip length. The team got into a good groove, executing run after run. Here you see them executing an 8-inch inflation run, and it went smoothly. 10-inch inflation runs proved to be difficult to set up, and the rocket struggled to achieve much distance. During later video review, the team attributed it to several factors. The mass of the additional air was too great, the propellant tubes, or straws, restricted the airflow and didn't allow enough acceleration, and a potential slow spot on the track as it dipped or sagged. The team reassessed and decided that 10-inch inflation runs were not achievable by their rocket. They decided to go ahead and make a set of 4-inch inflation runs, and in the end, even those short 4-inch inflation runs were a source of great joy as the team reached their final goal. Here we see the completed data capture sheet. Both sections provide some guidance, but require the teams to make judgment calls on how to fill them out based on how they executed their experiment. This team chose a line graph, which draws attention to the consistency of their runs. Reflecting back to Rob Stevenson's TED Talk in Module 1, he describes kids that just can't get enough. They just keep chewing on the problem even when they go home. Well, Luke proves this is true as he continues trying additional methods to accomplish the task. I too couldn't resist playing around and set up a rocket similar to the one in the original activity, but with minor modifications. As my rocket was much lighter, the results were good. Okay, I guess that's about it. I hope you enjoyed the video and saw how this action-reaction rocket activity could work into your classroom curriculum.